Good morning, everyone. Myself, Shweta, lecturer chemistry at Government Senior Secondary Smart School, Pind Malot, District Shri Muktsar Sahib. My today's topic is khoularuschs law of independent migration of ions. First question that arises in our mind is how to measure the limiting molar conductivity? And the obvious answer is it is measured by khoularuschs law of independent migration of ions. Khoularuschs law of independent migration of ions states that limiting molar conductivity of an electrolyte can be expressed as the sum of the limiting ionic molar conductivities of the cation and the anion, as it is shown in the given PPT. Lambda 0 of NaCl is equal to lambda 0 of sodium ion and lambda 0 of chloride ion. This law also states that every ion makes a definite contribution towards the molar conductivity of the electrolyte irrespective of the other ion with which it is attached. In general, if an electrolyte on dissociation gives new positive cations and new negative anions, then its limiting molar conductivity is given by the equation shown here. With the help of khoularuschs law, let us calculate the limiting value of molar conductivity of an electrolyte from the given data. We are provided with molar conductivity of calcium ion and the molar conductivity of chloride ion, and we are given to calculate the molar conductivity at infinite dilution for calcium chloride. So, first of all, come to the equation. Lambda 0 of calcium chloride will be equal to the sum of contribution of the limiting value of molar conductivities of calcium ion and twice the molar conductivity of the chloride ion. Let us discuss some applications of the khoularuschs law to know what is the use of this khoularuschs law. As we know, it is not possible to determine the value of limiting molar conductivity at infinite dilution for a weak electrolyte by extrapolation of lambda versus square root C graph. But this can be calculated very easily with the help of khoularuschs law. Coming to the first application, that is calculation of molar conductance at infinite dilution for weak electrolytes. Let us calculate the limiting molar conductivity for acetic acid. According to khoularuschs law, limiting molar conductivity of acetic acid is equal to the sum of contribution of lambda 0 acetate and lambda 0 hydrogen ion. This equation can be obtained by the knowledge of molar conductivity at infinite dilution for some strong electrolytes containing the same common ion. For example, consider the strong electrolytes HCl, NaCl, and CH3COONa. From khoularuschs law, we obtain the equation as shown. Adding the molar conductivity at infinite dilution for acetate ion, sodium ion, hydrogen ion, and chloride ion, and then subtracting the molar conductivity at infinite dilution for sodium and chloride ion, we can very easily calculate the molar conductivity at infinite dilution for acetic acid. Here is a numerical in which we are given with molar conductivity at infinite dilution for NaCl, HCl, and sodium acetate, and we are to calculate the lambda m0 for acetic acid. It very easily can be calculated by adding the molar conductivities for HCl and sodium acetate and then subtracting lambda 0 for NaCl from them. The answer comes out to be 390.5. Second application is calculation of degree of dissociation of weak electrolytes. Molar conductance of a weak electrolyte depends upon its degree of dissociation. Higher the degree of dissociation, larger is the molar conductance. With the increase in dilution, conductance increases, and at infinite dilution, the electrolyte is completely dissociated, so the degree of dissociation becomes 1. That is, lambda becomes lambda 0 when concentration tends to 0. Thus, if molar conductance of the solution at any concentration and the molar conductance of the solution at infinite dilution is known, then we can very easily calculate the degree of dissociation by the above formula. Alpha is equal to lambda at any concentration by lambda at infinite dilution. In this numerical, we have to calculate degree of dissociation of acetic acid